Wait, in the middle of Egypt's Sahara, an enormous waterway cuts through a landscape where almost nothing should be growing. Something enormous is moving through the Sahara, and the desert itself seems to be fighting back. Then, through the dust, the machines appear, moving thousands of tons of earth with astonishing force. But this isn't simply excavation. Entire sections of the desert are being torn apart and rebuilt. And when darkness arrives, the operation doesn't stop. It becomes even more intense. And then the camera pulls away, revealing that everything we've seen is only one piece of something far larger. And the scale is enormous. Egypt plans to reclaim 2.2 million feddans of desert. But why does Egypt need to transform so much barren land into farmland? Egypt's people and farms are concentrated along the Nile, while vast deserts remain unused. So when the country needs more farmland, where can it go? Egypt needs more farmland and settlement space, but land and water are limited. And beyond the Nile, one resource changes everything: water. And unlike the desert itself, water cannot simply be expanded on demand. Every new field creates another demand on an already limited resource. That is why Egypt's desert expansion is ultimately a water engineering project, not simply a farming project. The answer is more complicated than simply drawing another line from the Nile. Egypt is assembling several parts of a much larger water system. One important source is agricultural drainage water, which can be collected, treated, and reused instead of simply allowing it to leave the productive system. But drainage water cannot simply be pumped onto new fields. Treatment has to remove contaminants before the water can safely re-enter the agricultural system. Treatment is only one step. The water still has to be lifted, transferred, controlled, and delivered across infrastructure built for the desert. And now the real engineering problem comes into view. This water must cross enormous distances before it can become productive farmland. But there is an important correction. Egypt's official description is 2 water transfer routes, each 150 kilometers long, not a single 310-kilometer river. Even at 300 kilometers, the distance is enormous. A water network stretching across desert on a scale that demands an entirely different kind of infrastructure. And the destination is equally ambitious. The wider New Delta project is planned around agricultural development, covering about 2.2 million feddans. But 2.2 million feddans is the wider project footprint. Individual agricultural projects within it have their own targets, phases, and construction schedules. But this soil did not become productive by itself. It has to be prepared, irrigated, drained, and carefully managed to support crops in the desert. And beneath the farmland is another system entirely. Roads, electricity, pumping stations, treatment facilities, and water networks to make desert agriculture possible. So before the desert can become farmland, engineers face the question that controls everything. Where does the water actually come from? The New Delta system is designed around more than one water source, combining water management, treatment, transfer, and reuse, rather than relying on a single channel. Agriculture itself becomes part of the water cycle. Drainage water can be captured, treated, and redirected, reducing the need to discard usable water. At the treatment plant, that water enters a completely different world. Screens, basins, filtration, disinfection, and pumps working in sequence. Once treated, the water still has to travel through a vast engineered network before it ever reaches the crops. And that journey is where the real challenge begins. Treatment solves one problem, but it creates the next. Now the water must be moved through a desert where natural gravity offers very little help. A pumping station is essentially the engine of the system, adding energy to the water so it can continue moving through the network. But pushing water through hundreds of kilometers of infrastructure takes energy, and every pump becomes part of the project's long-term operating equation. Inside the pipeline, the water also loses energy to friction, so engineers must balance pipe size, flow rate, pressure, and pumping power. And above ground, the desert brings another challenge. Extreme heat can increase water losses through evaporation and stress the infrastructure itself. That makes flow control critical. Valves, pressure monitoring, and pumping stations must work together to keep water moving at the right rate. After treatment, pumping, and controlled transfer, the water finally reaches the landscape, where the entire system is meant to produce something: crops. But water alone cannot make desert soil productive. Before planting, the land has to be graded, prepared, irrigated, and managed for the crops it will support. Once the land is shaped, irrigation becomes the bridge between the water network and the root zone beneath each field. And this is the point of the entire system. Water that once needed treatment and transfer can ultimately become part of a new agricultural landscape. But turning desert green is only the visible part of the challenge. Beneath those fields, water and salt can create problems that take years to appear. That is why drainage matters almost as much as irrigation. Excess water has to leave the root zone before salts can accumulate and damage productive soil. In a water-scarce country, the goal is not simply to use water once. The larger strategy is to capture, treat, move, and reuse it wherever possible. And this is no isolated farm experiment. Egypt is building a connected agricultural landscape on a scale measured in hundreds of thousands of hectares. But expanding agriculture also expands everything behind it: roads, power, irrigation, drainage, treatment, pumping, and maintenance. But water does not move across a desert by itself. Every major transfer depends on pumps, pipes, electricity, and carefully controlled pressure. Inside those pipes, pressure is doing the invisible work, pushing water through long transfer routes and keeping the flow controlled from one stage to the next. The farther the water travels, the more carefully engineers must manage friction, pressure losses, elevation changes, and the reliability of every component. And when the route climbs, gravity works against the pumps. Water must gain enough energy to reach the next stage without destabilizing the system. A system this large cannot depend on one machine working perfectly. Pumps, valves, power systems, and controls all need monitoring, maintenance, and redundancy. Once the water reaches the agricultural zone, the next challenge begins: delivering it evenly across land that was never naturally designed for intensive farming. That makes drainage just as important as irrigation. Water that crops don't use has to leave the root zone before it becomes a long-term problem. And that contrast is the point. The cultivated land may look green, but beyond its boundaries, the Sahara remains almost exactly what it was. From above, truth appears. Egypt is still trying to expand agriculture across a desert far larger than any single farm. But before crops can grow here, the desert itself has to be engineered. The land must be graded, prepared, irrigated, and made ready for cultivation. Getting water to a farm is only the beginning. Engineers must distribute it across thousands of individual growing areas with enough precision to avoid wasting a scarce resource. There is another threat hidden beneath the surface: salinity. If irrigation water evaporates and leaves salts behind, productive soil can gradually become harder to farm. That is why drainage matters so much. It helps move excess water away from the root zone, reducing one of the pathways through which salts can build up. In desert agriculture, irrigation alone is not enough. The soil must also be managed so roots can access water without allowing salts and excess moisture to accumulate. A desert farm is therefore more than a field. It is a connected system of water delivery, drainage, roads, power, soil management, and constant monitoring.
Machines can prepare the land, but agriculture still depends on decisions: what to plant, when to irrigate, and how to use every unit of water.
In a water-scarce country, expanding farmland creates a difficult calculation. Every new hectare must justify the water, energy, and infrastructure needed to keep it productive.
Here, wasted water is more than an inefficiency. It can increase pumping demand, complicate drainage, and make the entire agricultural system harder to sustain.
What looks like a simple green field from the air may actually depend on kilometers of hidden infrastructure beneath and around it. But creating farmland is only half the challenge. The bigger question is whether Egypt can supply enough water to keep these new agricultural areas productive over the long term. Egypt's water is already under pressure from cities, farms, industry, and environmental needs. Expanding agriculture therefore adds another demand to a resource with little room for waste. And water does not move through this landscape by itself. Pumps, electrical systems, pipelines, and control equipment must keep the flow moving whenever gravity cannot do the job. The more water the system moves, the more energy the infrastructure can require. That makes pumping efficiency part of the agricultural, not simply an engineering detail. Heat adds another complication. Water exposed to the desert atmosphere can be lost through evaporation, making efficient delivery and careful irrigation even more important. For the farmer, water is useful only when it reaches the crop at the right time. That turns a giant water network into a problem of timing, control, and precision. A system this large cannot simply be switched on and forgotten. Pumps, canals, pipelines, valves, roads, and drainage networks all require inspection and maintenance.
Challenge is reliability. A failure in one component can interrupt water delivery, forcing engineers to detect problems quickly and keep critical sections operating.
And beneath every pump, canal, and irrigation line is the question that none of the machinery can solve. Is there enough water available to keep expanding the system? That is the real test of Egypt's desert expansion. Whether the entire system can remain productive under tomorrow's water, energy, and environmental pressures. The engineering is real. But engineering a system does not automatically answer whether its long-term water balance makes sense. Every new hectare brought into cultivation creates another permanent demand for irrigation. The challenge is balancing expansion with the water that can actually be supplied. There is another question. After irrigation, where does the water go? Drainage determines whether excess water becomes a resource, a problem, or part of another treatment cycle. When suitable drainage water can be collected and treated, it may become part of a broader reuse system. But treatment quality and water chemistry determine where that water can safely go. Treatment can remove contaminants, but it does not make every water source identical. Salinity, chemistry, and the intended use still determine how the water can be managed. Large-scale desert development also changes the landscape itself. Water, soil, drainage, environmental consequences that must be monitored. Official project targets describe enormous agricultural ambitions. But targets are not the same as completed farmland, and planned capacity is not the same as water already being delivered. And this brings us back to the number that made the project famous online, 310 kilometers. But that figure should not automatically be interpreted as a literal artificial river. The distinction matters because a route length, canal length, pipeline network, and agricultural measure completely different things. Mixing them can make a project sound different than it really is. The answer is more complicated than a single river. It's a connected system of treatment, pumping, irrigation, drainage, and farming, built in stages. But water alone does not create a farm. It must be delivered through irrigation, managed in the soil, drained correctly, and matched to crops that can grow there. This is the physical evidence of the transformation: soil that can hold moisture, roots that can grow, and crops sustained by an engineered water system. And the contrast is important. The surrounding desert has not disappeared. Productive land exists inside it. From the ground, you see crops. From the air, you see the real engineering story: a network, water, energy, treatment. Behind every green field is a system that never really stops. Water must keep moving, equipment must keep working, and farmers must keep managing the land. The landscape itself can change the calculation. Heat, evaporation, soil conditions, salinity, and maintenance all influence how efficiently water becomes productive agriculture.
Egypt has demonstrated that desert agriculture can be engineered. The harder question is whether the infrastructure can remain productive as water pressures continue to grow.
So the future of Egypt's desert frontier may depend on a delicate balance: producing more food without demanding more water than the system can sustainably provide. Egypt's experiment is no longer simply about making the desert green. It is about discovering how far engineering can push agriculture before water becomes the limit.